Hello dear students. This time I am going to discuss with you what are exact differential equations, what is their solution, and how you can identify the exact differential equations. You see, I want to just review what you have done before the exact differential equations in your UG undergraduate courses or BTech students. You know the first order and first degree ordinary differential equations. You have ordinary differential equations. How you solve them? Method of solutions. In method of solutions you have done variable separable method. Variable separable method you did the homogeneous method, homogeneous differential equation of this order. We are discussing this with first order and first degree differential equations. In homogeneous method, you make some substitution, then you convert this into the variable separable method. Then you have third one, a linear differential equation like dy by dx plus py is equal to q. How you solve it? Where p and q are functions of x alone or can be constants. You know, we solve it by integrating factor, e raised power integral of p dx. Or if it is dx by dy plus px is equal to q, where p and q are functions of y alone. Their integrating factor is e raised power integral of y dy. You have done this one. Or you have also done this dy by dx plus py is equal to q y raised power n. It is Bernoulli's differential equation. Bernoulli's. By suitable substitution, you convert Bernoulli's differential equation into this, and then by some substitution, by integrating factor, you come by variable separable method. These are the cases you did. Now, sometimes you say, where I do not agree with this, you write that if a differential equation is not solvable by variable separable method, or is not of this form, then we try it for exact. This is not the case. Exact differential equations are the type of equations which can be solved by exact method. Sometimes there you will come across a differential equation where you can easily separate the variables, and at the same time you can solve it by exact method. There are differential equations which is of this form. You can solve it by both, by this method and some. And there are some differential equations of the first order and first degree which cannot be solved by this, not solved by this, not solved by this. We try for exact. They can be solved by exact. And there are some differential equations which cannot be even solved by exact method. And what we do there, we find integrating factor. Those are known as reducible to exact form or reducible to this form. So this is a method. Before defining this, what this exact differential equation is, let me introduce, before definition, I will consider a differential equation. You see, let us consider a differential equation. Say it is sec square x tan y dx plus tan x sec square y dy is equal to 0. This is a differential equation. You can easily solve this differential equation by variable separable method. You can solve it by variable separable method. That is, you take dx, with dx you take the x terms, and with dy you take the y terms, then integrate both sides, add constant on one side. This is the variable separable method. But I say that this differential equation is also exact. How it is exact? You see, if I name this one, I say there exists a function. There will exist a function. Which function? Say u, it is u is equal to phi of xy is equal to tan x tan y. Tan x tan y. First of all, I will review your advanced calculus. In advanced calculus, I will write here a formula that you have done, or you may be doing it in advanced calculus. You have an advanced calculus concept. I will review here, right here, from advanced calculus. You have, if u is equal to, say, psi of xy, or you can write psi of xyz. You have a total differential, exact differential. It is du, you write. It is partial of psi with respect to x into dx plus partial of psi with respect to y dy. It is the fundamental theorem on total differential. Or if you have, you can write this also, du is equal to del u by dou x into dx plus dou u by dou y dy. You can write this way also. If you have a function this of three variables, x, y, z, then you can extend this theorem. This is the theorem on advanced calculus. You can write del u by del x dx plus del u by del y dy plus del u, dou u by dou z dz. This is the fundamental theorem. We can use it here. You see what we do. I will find here partial derivative of u with respect to x in this case will be tan square x, tan x square x, this is constant, sec square x, this is sec square x, sec square x tan y. Then partial derivative of u with respect to y is, it is tan x into sec square y. Applying this formula, if I apply this formula, you see what happens. What will you get? You write du is partial of u dou u by dou x dx plus dou u by dou y dy. That is du is, use this is sec square x tan y dx plus tan x sec square y dy. So what you have got? You could write this differential equation that you took first. It is the total differential, or we say exact differential of what? You can write given differential equation, which was this first, which was your first. Which was your first differential equation. Given differential equation, that is secant square x tan y dx plus tan x sec square y dy. You could write it d of, that is total differential, exact derivative of what? It is an exact derivative of tan x tan y. So given differential equation is the exact derivative of some function of x and y. What was that? Tan x tan y. So by definition, we have not yet given you the definition. I am just giving you the introduction. It is just what? Introduction of your exact differential equation, not definition yet. It is an introduction. So given differential equation, we could write it is a total differential of what? Tan x tan y. So by we say it is exact. You take one more example, you see. I will give you one more example. I will write here, say it is sine x, sine y. That you will come to know later on. I consider second example. Consider first order differential equation. I will consider first order differential equation. I will write it as cos x sine y dx plus sine x cos y dy is equal to 0. This is a differential equation. You can also solve it by variable separable, because you can take dx on one side, dy on another side, then take x terms on with that dx and y terms dy. You say you can solve it. But I will say that this differential equation is exact. I will say it is exact. Why it is exact? Because there exists a function. A function. What is that? That is u, or function of xy, which is sine x, sine y, such that given differential equation, it is cos x sine y dx plus sine x cos y dy can be written as derivative, total differential of what? Sine x sine y. When you apply the total differential for this, you will get this differential equation. So given differential equation can be written as the derivative, the total differential, the exact differential of what? Sine x dx. You know, if we take u is equal to sine x sine y, you will get partial of u with respect to x is what? Cos x sine y. You will get partial of u with respect to y. What is it? Sine x cos y. So when you use the total differential formula, du, what is that? Del u by del x dx plus del u by del y dy. Do you follow? So when you use it here, you will get d of u is your sine x sine y. It is your cos x sine y dx plus sine x cos y dy. So what is this? You could write the given differential equation, this as the total differential of what? Sine x sine y. We say it is exact. So although this was very easy to solve otherwise by variable separable, but sometimes there are differential equations. I will give the example of that also. I will write here, say, third example. Consider a differential equation, first order in fact. Say it is I will write it as sine y plus y cos x dx plus x cos y plus sine x dy is equal to 0. You look this differential equation. This is my differential equation. This is my differential equation. This differential equation is such, this cannot be solved by variables separable method, nor homogeneous method, nor can be reduced to, this cannot be reduced to variable separable method by appropriate substitution. You cannot reduce it, this differential equation. Which is a previous two examples I have given you, that those were the differential equations that you could solve by variable separable method, okay? And I have told you that those two differential equations possesses what? A peculiar condition, a peculiar property, that we could find out a function in x and y such that the differential equation can be written as exact derivative of that function of x and y. Second example is also, this is also a differential equation. We cannot solve it by variable separable method, and we cannot solve it by homogeneous method. We cannot find any what is known as substitution that will reduce to this. But still I say that it is an exact. So what can we say? We can say there are some differential equations which can be solved by variable separable method and can be exact. There are some differential equations which cannot be solved by variable separable, may be exact. So there is no, some books write that when the other methods fail, when variable separable method fails, when homogeneous method fails, when LD method fails, that one is dy by dx py is equal to q, where you find out integrating factor. When that fails, some say when Bernoulli's method say fails, we have the exact. That is not the same. There are some differential equations you can solve by all the methods. There is no hard and fast rule that when all the previous methods fail, then you have exact. No, exact is a type of differential equation. It is a type of differential equation which satisfies the condition that this differential equation can be expressed as the total differential of some function of x and y. That is known as exact. I have not given you that definition. I am just giving you the introduction. You see, this is a differential equation which you cannot solve by variable separable method or other methods, but I say it is exact. How I say it is exact? I will say there exists a function. There exists a function in x and y. What is that? That is, say u is equal to some function of xy, which is x sine y plus y sine x. Such that total differential, exact differential of this comes out to be this. You see, I find our partial of u with respect to x comes out to be sine y plus y cos x, and partial of this with respect to y comes out to be what? X cos x plus sine x. Do you follow? When I write the total differential formula, it is du is partial of u with respect to x dx plus partial of u with respect to y dy plus partial of u only, which is two variables. Note, you can have the exact differential equation of three variables when you go in PDE, partial differential equations. These are ordinary partial differential equations. These are ordinary differential equations. Then we have partial differential. There you can have the three. You see, what is this d? It is total differential of this x sine y plus y sine x. It is the differential equation now. This differential equation. This is sine y. This is sine y. The value of dou u by dou x, sine y plus y cos x dx, then plus x cos y plus sine x. It is dy. So we could write our differential equation as the exact derivative of some function. What is that? X sine y plus y sine x. We say it is an exact differential equation. This is exact differential equation, the introduction of that. Now we will give you the definition, the formal definition of exact differential equation. Let us have. Okay, students, let us have the definition. This is definition of exact differential equation. of course of first order and first degree. Exact differential equation. How we define? We say a differential equation of the form m dx plus n dy is equal to 0, where capital M and capital N are functions of x and y, where capital M and capital N are functions of x and y, is said to be exact. It is said to be exact if there exists a function in x and y, say u is equal to some function of xy, such that differential equation number 1, that is this, is exact differential of u. That is what you say, your differential equation m dx plus n dy is the total differential of u, which you took d of derivative of psi of xy. This is now definition of exact differential equation. I have given you previously 3 examples. It is just introduction. What is actually exact differential equation? Exact differential equation of this form. This is a function, some function of x and y. This is some function of x and y. M dx plus n dy is equal to 0. We say it is exact if you can find some function in x and y such that this is the total differential of that, exact differential of that function. But to find out this function sometimes directly is very difficult one. Just as you have seen there in 3 examples, previous 3 examples, you cannot directly find out that function of which this given differential equation is the exact this differential. For that we have a theorem, a necessary and sufficient condition theorem, that gives you the identity of the differential equation when it is exact. That is how can you recognize that a particular differential equation is exact. For that we have a theorem. I will state and prove that theorem for those students who have this exact differential equation as a in syllabus, actually UG syllabus, University Grants Commission syllabus, which is scattered over all the universities of India. In UG classes, that theorem forms the part of syllabus. That is, you have to prove that theorem. But in case of BTech classes, engineering classes, where they have the exact differential equations, they have to apply that. They have the application of that theorem. That is when to recognize, when to identify the differential equation is exact. Once you pick up that the given differential equation is exact, you can at once write out its solution. That is one thing. And in case of UG students, undergraduate class students, they have to this prove the theorem, prove the condition, what is the necessary and sufficient condition for a differential equation to be exact, and then apply. Let us have very important theorem, then you will enjoy the beauty of this exact proof of the theorem. It is a very simple, very interesting theorem. This is actually the condition of exactness. I will state the theorem. This is the theorem. This is the theorem. It states the necessary and sufficient condition for the differential equation which is m of dx plus n dy is equal to 0, where you know m and n are some functions of x and y. This is the differential equation. Now when can we identify what is the condition for identification of this differential equation to be exact? How can we recognize it as an exact? We have given you the definition of exact, what is definition of exact differential equation. Now we have to first recognize it, identify it, then we can easily apply the solution, which is the solution for the exact differential equations. You see, the condition is the necessary and sufficient condition for the differential equation m dx plus n dy is equal to 0 to be exact. Exact is partial derivative of m with respect to y must coincide with partial derivative of n with respect to x. Dou m by dou y must be equal to dou n by dou x. What is m? It is the coefficient of dx, function of xy. What is n? Coefficient of dy, function of xy. When this coincides, so whenever we are given a differential equation, we want to see is it exact. What we do, we find out partial of m with respect to y, which is this, partial of n with respect. If they coincide, we will write they are exact. Actually, this is the necessary and sufficient condition for this if and only if condition. We will have the proof of this. Let us take the proof. In proof, we have necessary condition. How we proceed in necessary condition? We will write, consider that differential equation m dx plus n dy equal to 0. We consider this differential equation m dx plus n dy is equal to 0. Now necessary condition we will take for granted, let this differential equation be exact. Suppose given differential equation is exact, that means we are taking this part for granted, let it be exact. We will prove when it is exact, this will follow. Partial of m with respect to y will be equal to partial of n with respect to. Conversely, we will write then conversely, if this differential equation is such that it satisfies this condition, if it satisfies this condition, then we will prove that it must be exact. Here you take it is exact. When you say it is exact, so by definition, m dx plus n dy is what? Is exact differential of some function in x and y. Some function in x and y. What does that mean? Well, that means there exists u is equal to psi of xy, say, such that m dx plus n dy is what? It is total differential of u, which is equal to d of psi xy. Name it second. Because you said that it is exact. When it is exact, it means there is some function in x and y. There is some function in x and y such that this is equal to this exact differential of that. Now what is actually we know by advanced calculus what is du. It is partial of u with respect to x dx plus partial of u with respect to y dy. I have quoted that example, this theorem it is advanced in advanced calculus, this theorem. Fundamental. This guy is true for 2 variables, also true for 3 variables, so on. So if we name this third, let us name this equation third. From second and third, what you get? It is m dx plus n dy is partial of u with respect to x dx plus 2y dy. Now this is the equality of partials. You can also have the equality. By equality you can say, option top, this is this. You can say your m is del u by del x and your n is del u by del y. So if we differentiate this partially with respect to y, what you get? Dou m by dou y is dou 2u by dou y dou x. Name this alpha. If you differentiate this now partially with respect to x, it is partial of n. Dou n by dou x is what? Dou 2u by dou x dou y. When you differentiate this partially with respect to x, this is equation beta. Let it be beta. So from since you have this result, since we have dou 2u by dou x dou y is always equal to dou 2u by dou y dou x. There are some conditions for this second order differential mixed partial to be equal. It is known as Young's and Shivas theorem. What Young's and Shivas theorem satisfy the conditions there, what you for this u should satisfy the condition, those conditions are already satisfied here. So we can say this is equal to this. When this is equal to this, from alpha and beta, what we get? We have partial derivative of m with respect to y is partial derivative of n with respect to x. So we have proved when the given differential equation is exact, it satisfies this condition. Partial of m with respect to y is equal to partial of n with respect to x. This proves the necessary condition. So when a differential equation is exact, it must give you dou, you may sometimes say dou or partial or del, okay, it is one and the same. It is dou of m with respect to y is dou of n with respect to x. So you can identify this when this condition is satisfied for a given first order differential equation, first order and first degree in fact. So you can say it is exact. But what about converse? We have to go to the converse part. This is the converse part. Converse. It is sufficient condition. Sufficient condition. What we say in sufficient condition? We write let differential equation m dx plus n dy is equal to 0. Let us name it fourth. M dx plus n dy is equal to 0. Such that, let it be such that partial of m with respect to y is equal to partial of n with respect to x. We are taking this differential equation is such that it satisfies this condition. Now my dear students, I have to also give the proof of it is second part, that is sufficient condition. This it will be the first video on exact differential equations. For second part, you will have the sufficient condition. Second video, I mean exact differential equation. You will have the proof of this sufficient condition. You will see there. proof of this sufficient condition, and some applications, method of solution, how you solve the exact differential equations. And with this, I will end this video. Thank you very much, and be with me in this second video on exact differential equation. Thank you very much, and take care. Thank you.